As an FYI, Natasha Neogi was a professor at University of Illinois when I got hired here in 2008, and we had some nice time together. Then later she decided to move to NASA and to be more important for directing our research. So with that, Natasha, I'll pass it to you and just take the stage, please.
Thank you so much, Naira. It is a pleasure and privilege to be invited to chat with you all today. This is an informal presentation. I've given it, I think, or a similar version of it 2 or 3 times before to the FAA, to the RTCA, and to EASA. So don't hesitate to jump in and stop me, and we can chat during it. I also want to say that this presentation is, it's got my name on it. I'm NASA's senior technologist for Assured Intelligent Flight Systems. The complement to Dr. Gregory's wonderful position, which is more in controls, but it's really an amalgamation of the research and opinions of an entire project, if not a mission directorate, system-wide safety project. I cannot thank those folks enough, including Paul Miner, Jeff Madeline, Frank McCormick, who's a former Boeing DER, Sarah Lehman, Steve Young. I could go on, Misty Davies, Nikunj Oza. So again, a conglomerate of work in here. So we'll be talking about integrating or developing AI or ML components, and then perhaps fielding them in civil aviation. Specifically, we'll dive into some challenges and barriers. Very, very rough outline here. A little bit of motivation and definitions. Why are we here even talking about AI and ML when it's hard to certify regular aircraft systems and get them into the NAS? And then we're going to dive into a key question, which stops most AI or ML components or implementations from actually transitioning into live flight, which is what constitutes sufficient evidence that an ML implementation of a specific function meets its requirements. And if you can answer that, you're well on your way to being able to talk to the FAA and say why your system is ready and able to be fielded. Finally, we'll talk about some high-level questions which may need some more research and potential paths forwards to these systems to getting into the airspace. And I didn't start my timer. Okay, I started my timer. I'll remember I'm at about 2 minutes in. So some motivation and definitions. Why are we here? Why are we chatting about this topic? A couple of you may have seen me give this presentation before, so you'll probably know that this is the interactive part of the presentation. Most people know that I'm in, looking at safety for commercial or civil aviation. So when I ask the question, what do you think the safest form of transportation is? Everyone sticks up their hands and says, commercial aviation, thinking, no brainer. This is what she's here to talk about. And then normally I ask people, well, let's vote on it. Who thinks it's cars? Who thinks it's planes? Who thinks it's trains? Who thinks it's boats? And we get a bit of a spread. We've got a bunch of people who think it's trains because they're maybe in Europe or Japan and they know trains are very safe there. And then a lot of people saying, yeah, no, it's civil aviation. We're in an aero department. Why are you asking us this? And that's because it's actually not correct to say that commercial aviation is the safest form of transportation there is. It's actually lifts. Lifts essentially carry over 2 billion passengers a day, over 100 millions of vertical miles in over 200 nations. And essentially, the air statistics or the accident statistics are about 30 people a year die associated with lifts. And about half of those, 14 of them, are folks who are maintaining the lift. They're not even riding the lift. They're, fixing it. So about maybe 14 or 15 people at most die in lifts. And you can see the enormous number of vertical miles traveled. Now, lifts themselves, they're not new. Lifts go all the way back to the 1850s. But they go back well before the 1850s to Archimedes or even before that. But they didn't catch on until the 1850s. And most people say, oh, that's because of electricity. It's like, actually, in the 1850s, you didn't have a lot of electrified things. And it isn't because of electricity that lifts didn't catch on. Lifts began catching on in the 1850s because in 1854, a fellow named Elisha Otis went to something called and I always have to look this up so you can see me kind of looking at a sheet of paper, the exhibition of the industry of all nations, which I like to call, the equivalent of a World's Fair, in October of 1854, and demonstrated his new invention. He essentially installed a hoisting platform. You can kind of see that in the picture in the bottom, and a series of guardrails, hoisted himself up about 50 feet in the air, and then had the hoisting cable cut. And instead of dropping 50, feet to a gruesome end, the platform dropped only a few inches. And this demonstrated Elisha's, interesting invention, which is essentially a safety device. It was a flat leaf cart spring, which remained bowed when the hoisting cable was in tension. But when that tension disappeared, the cart spring, flattened out, and it managed, of course, to catch the platform on notches, which were carved into the guide rails of the lift, essentially. And this, of course, made a great impression on folks and raised public awareness of the fact that these particular platforms, could be made safe in the face of this enormous hazard or catastrophic failure. And he began getting the first orders for lifts for freight just a year later. And then in 1857, I believe, the first orders for passenger carrying lifts came about and were installed in downtown New York in department stores. And this is why when you walk into a lift today, you'll see Otis elevators. Now, the thing to keep in mind here is Elisha Otis did not invent elevators. He invented that device by which the safety of that lift could be assured in the space, in the face of that enormous or catastrophic failure of loss of tension in your hoisting rope or platform. Now, why have we just spent, looking at my timer, about 3 or 4 minutes talking about lifts when we're supposed to be talking about AI and ML? Well, the inability to establish appropriate assurance for AI or ML implementations of functions leaves us unable to effectively manage their risks and benefits. This drives the cost of development uneconomically high, delays deployment or adoption of these machine learning or AI systems at scale in safety-critical contexts, and results in unknown and unmanageable risks. So our goal is going to be to discover and define what constitutes sufficient evidence to substantiate a safety claim related to an AR and ML implementation of a function performing a safety-critical role in obviously a mission-critical context. And this is because I firmly believe, now the bang box is my opinion, but it's probably a well-accepted opinion. ARML is not going to see widespread adoption in safety-critical aviation systems until it's properly assured. So that flat leaf cart spring, that's actually more important than the function itself. Without it, no one's going to actually buy it or want it. And in case you doubt the transformative power of lifts, just like AI and ML is going to be transformative, please remember that every single cityscape is predicated on the existence of that flat leaf cart spring. Without lifts, you don't have skyscrapers. All right, this slide probably a little less interesting for the rest of you, but I did mention the word standards in my title. We want to remember standards are very important, but standards are essentially built around consensus, and they require stakeholder consensus for the need of that standard, as well as a commitment to support development of that standard and then to apply it. So you need to really have a broad section of stakeholders if you want to come up with a new standard, for instance, perhaps around something like, how do you implement ML in safety-critical contexts? So if let's say you have your ML implementation of a portion of an autopilot that you want to put on a large commercial transport aircraft, you're going to want to involve a lot of people in it, not just AI/ML people and not just avionics people. You're going to need to want to talk to pilots, to controllers, to aircraft equipment manufacturers, as well as avionics equipment manufacturers. Those are two different things, remember. The FAA, other regulators, R&D, and enormous amounts of consultation with public as well. If you don't have a critical mass of your stakeholders, you're going to end up with a standard which is not going to have a lot of impetus for uptake. which is a very fancy way of saying no one is going to use it, even if you get it through. Please remember, we need to understand the limits of what current processes and metrics can provide with respect to new technologies. When you're developing your standard, you not only have to understand deeply the fundamentals of the problem that you're hoping to solve, but also the underlying technologies that you're going to be deploying in its reference implementation, as well as the verification technologies used in assuring that reference implementation. If you don't understand the science behind the problem, as well as the implementation, the V&V technologies, you're going to have trouble putting together a standard. What does NASA do for you? NASA provides SMEs to help create standards, provides relevant findings from their R&D activities. And, if we hear of gaps or challenges, we can then start up or change our own R&D activities and lead to a collaboration, perhaps, between interested parties to fill those challenges. Okay. That was a long beginning, but now I've hopefully gotten you in the safety frame of mind, because I know we're all excited about using ML, but now we're thinking about safe ML. I've been talking a lot about AI/ML. I stumble over it. AI and ML are two different things. I've splatted two definitions up there, which I pulled from old course notes from MIT that anyone will recognize. Roughly speaking, AI, you can think of it as machines that learn, reason, and potentially act for themselves. Machine learning, a little bit more tightly, is the use of statistical techniques to analyze data and create algorithms that can generalize to unseen data without explicit programming. There are other things which go in that too, but I'm going to keep that short for time because most of you know what ML is. Please look at the circles on the side. You can see machine learning and AI are not the same thing. One is a subset of the other according to that diagram. Data sciences is overlapping and off to the side. I've got friends who say it should be completely over top of it. Again, we can all chat about that because this is still evolving, and the overlap is dependent on how you define data management. So again, this is what I mean when I say machine learning. I'm pretty much going to talk about machine learning for the rest of the presentation. I'm not really going to dive into AI except for this next slide. So AI is a multitude of things. It's not just machine learning, but also rule-based systems, search and optimization techniques, decision-making under uncertainty, as well as evolutionary strategy. And you can see a list of the techniques which can be associated with all of those words. And again, we can agree to disagree on it. Some people don't like putting search and optimization under AI. I like doing it. I chat with Ella Atkins a lot. She likes doing it. But again, this is evolving how the definitions go. But when I see AI, I do think of those things. I certainly think of rule-based systems, which we often forget about. ML. This one I'll spend a little bit more time about. We're going to be talking about ML for the rest of the presentation. When I say ML, I'm thinking about both supervised and unsupervised learning, as well as weakly supervised learning, reinforcement learning, and everybody's favorite new topic to talk about, generative AI, which include our autoencoders, our generative adversarial networks, our transformer networks, which include our GPTs, which are, again, generative pre-trained transformers, and BERTs, of course, which are bidirectional encoder representations for transformers. All of that stuff can be lumped into machine learning. Normally, we're talking about supervised learning when we're talking about safety critical contexts for aviation, but please remember the rest of the stuff that's there too. Now, as I define machine learning, some people say, but wait, we already use some of this stuff as well as some of that AI stuff as well in aviation today. And you're indeed quite right. The clearest example is the use of optimization tools during the design of the 787. Not only for the wing body design, but also for the composite materials used in it. Essentially, the reason we have that lovely 9.6 wing aspect ratio and that 32-degree wing sweep due to stochastic gradient descent methods for optimization. I have that straight from folks at Boeing. Similarly, they use stochastic gradient descent methods for composite material design. NASA uses it in the context of looking at ASRS, Aviation Safety Reporting Systems, data, so accident and incident data. And you can use large language models to parse through it to find positive contributions to safety. Similarly, we use it for anomaly detection and vulnerability discovery. So actively looking for indicators and precursors for anomalies and potential degradations in safety, and many, many, many others. As they say, this is no way complete. Everyone likes bringing up ACAS-X. We can talk about that if we want to argue whether that's ML or not. So it's here. It's here. It's being used in the context of aviation. So what are we going to do about it? You know, what are we going to do to tame the ML beast and make sure that we are going to continue having a nice, safe national airspace system? And the examples I talked about, of course, were what I like to call offline examples, in the sense you're using it in terms of design, or you're using it in terms of maintenance, or in terms of forensic analysis. And a lot of people want to use these machine learning implementation of functions in an onboard fashion, such that when your aircraft is flying, they're performing some sort of a function. If you want to do it that way, you're going to have to answer this question. What constitutes sufficient evidence that your machine learning component is going to meet its requirements? I've been talking a lot. I probably should stop to see before I jump into the answer to this question, or not the answer, but jump into thoughts on this question. Any questions, comments, concerns?
I guess no, just go ahead.
Okay, I will keep going, but if you have a question, don't hesitate to interrupt me, and
Sure.
we'll probably take them at the end as well.
Mm-hmm.
All right, so before we chat about what might be sufficient evidence that your machine learning implementation of a particular function is good to go on your aircraft, let's talk about aircraft certification. This is a topic that, as academics, we're not always, up to date on. So, aircraft certification, it's not a mysterious thing. Essentially, the primary aim of aircraft certification, which is found in 14 CFR Code of Federal Regulations, Part 21.1X, depending on what you want to do, is to provide safety assurance or assurance of safety by assuring that an item performs its safe intended function under any foreseeable operating condition, which is a fancy way of saying it always does what it's supposed to do under those foreseeable operating conditions. And two, assuring that unintended functions are improbable. And you can understand that that's probably a little bit trickier there. What you really need to do is you need to have a standardized and repeatable engineering process in place in order to demonstrate that you have met your certification requirements. If you don't, you're going to have to find another way to show that your function is doing what it's doing. Essentially, unless you can show that the means by which that item is developed is done so with an auditable process which generates the right artifacts, providing evidence that indeed all of those high-level aircraft properties have been traced down to those individual items, you're not going to be able to convince a regulator that, yes, your item is doing what it's supposed to do. And so I've been using the word item a lot and component a lot, just to get you in the mood. Aircraft certification works as follows. You start at the aircraft level. You have your requirements. You have some safety properties. You have some environmental assumptions. You refine them down to a subsystem level, and then you refine them down to an item level. Machine learning is an implementation. It's a piece of software that you've written or developed. It's always at the item level. And so you want to remember that. So you have to refine those aircraft safety requirements all the way down to what are their influences on that machine learning item. So there are ways to do this, traditionally. You take your requirements, you refine them down, you use the ARP 4761A, which is aircraft system safety, you use 4754B, which is avionics implementation, and then you use DO178C, which is, of course, your software implementation. Now you run into a problem because your machine learning software is essentially not amenable to the things you have to do in 178C. So you've got to come up with another way. You're going to have to come up with an argument why your machine learning implementation is indeed matching or meeting those high-level aircraft system safety requirements. There are a couple of ways to do this. I started thinking of, fancy slogans, assumptions, argument, and artifacts, or C's. I think it was context, claims, and concrete something or the other. Then I thought, no, as an academic, our best use in life is stealing someone else's idea and repurposing it. So I did so. I went and looked at some previous literature, and the 3 E's, now I've repurposed what they mean, are actually pretty good to go. Essentially explicit claims. Your required emergent properties have to follow from the combination of the properties of your system, component, the domain assumptions, environmental assumptions, and constraints. And they have to explicitly indicate the level of assurance claimed. Very fancy way of saying you have to come up with an actionable claim. You have to say this system in this context meets this target. Which, a specific example, this detect and avoid system in the context of a UAS in the National Airspace System of flying at Class G airspace meets essentially does not or detects or only misses 1 in a million aircraft of a certain size. So this system in this context meets this target. Evidence. When you run tests on your machine learning component, or when you run simulations, or when you would, even do maybe a formal methods proof, what you generate is an artifact. You don't actually generate evidence. So you generate millions and millions of test cases or millions and millions of simulation runs. Those are artifacts. Those artifacts are they have the potential to become evidence in the context of a safety claim. So you generate a thing. Whether or not it's evidence depends on what you're trying to prove. And it's normally a combination of testing, analysis, including modeling and sim, and appeals to process. Don't forget appeals to process, which is something you're going to have to do where you say, well, maybe this software which is deployed in the field is actually the exact same thing as software that you did the test and analysis under. If those two things aren't the same, what is the value of the test you've done? So keep that in mind when you're attempting to generate evidence of a safety claim that you are arguing is actually fulfilled. The last one, the most squishy, expertise. At this stage, you really do need someone who knows what they're doing. Your developers need to be familiar with the best practices and deviate only when needed. A true expert is able to tailor their approach to assuring a novel element with respect to the methods, languages, tools, and processes they use. So without that expertise, it's like doing a proof. You kind of work it down from the top, you work it up from the bottom, and then a miracle occurs in the middle. That expert knows how to streamline your proof such that indeed a logical series of steps can be seen as being followed. And as they say, you don't generate your safety claim at the end of designing your system. Your safety argument has to occur and be generated as you're designing the system. If you don't do that, you end up with a system which is a lot harder to assure than if you're trying to generate that argument while you're designing the system, because then you can build in the hooks such that the artifacts you need are going to be generated, and then you can evaluate whether or not they're going to qualify as evidence. So the 3 E's. You're going to have an explicit claim, you're going to have some evidence, you're going to have an argument that links them together, and then that expert is the one who helps create that argument that links them together. In reality, of course, you have your claims, you generate your argument, and then you collect your evidence. All right. What is this explicit claim I speak of? So before we jump into what this explicit claim is and how you want to tailor it so that you can actually come up with an argument for why it's true and then collect the evidence that shows that, we need to remember, and I know I'm preaching to the choir, safety is not an intrinsic property of a component or an item. So your machine learning component is not safe. A machine learning component can be correct with respect to its specification, but in the context of one system, it may be safe, and in the context of another system, it may not be. And that's because we understand safety is an emergent property. It occurs at that aircraft level. So your aircraft gets into an accident. Your machine learning component doesn't get into an accident. So please remember that safety is that high-level emergent property. That's why you have to refine down the implications, or project down what the implications of those high-level aircraft system properties are on that machine learning component interface. Sorry, was that a question? I will assume it may not have been. Okay, specifications of your machine learning component. That's what characterizes its behavior. Essentially, when you have your machine learning implementation, you're really only worried about the interface of that particular implementation with all of the other things it affects. And this is important because that really means you're only worried about what the requirements burden is on that particular item. You're not as worried about the internal implementation details, and that helps you a great deal. And it's important to realize that the specification of your machine learning component, which might be, identify Persian cats, is very different than the set of requirements which trickle down to that interface, which that machine learning component then has to obey. And that gap between the specification of that machine learning component and the set of requirements that it has to obey then needs to be bridged, and you need to show that hopefully that one is just simply a refinement of the other. But that gap is how that machine learning component interacts with the broader system, and thus eventually interfaces with the physical world. Important assumption to remember. If your component only meets its assurance criteria, if a human interacting with that system behaves in a certain way, this becomes an assumption on the environment of the component and must be evaluated for validity. These are, again, high-level words. Let me concretize it. If you assume there are two pilots in the cockpit who are performing as a self-checking set of pairs, as a self-checking pair on one another, that is an assumption. And it's an assumption that actually carries through almost every large commercial aircraft today. And it actually influences the avionics architectures we use. So the argument we currently use to have our triplex architecture be accepted as, meeting the safety, the level of safety we want, relies on both pilots into the cockpit. If we change that, we're going to have to rework from first principles our avionics architectures or our safety arguments. And this is not unique to a single company. It is across the board. It's in the military as well for their their quad architecture. All right. I just talked about assumptions. What is their role? Well, I mentioned that you have your machine learning implementation. Perhaps it is recognizing Persian cats. That's its specification. And then you have the requirements burden upon it. How do you show the bridge? Well, you want to take that machine learning component specification. You're going to have to, combine it with the set of domain assumptions or context assumptions that you have. Essentially, that's an explicit statement of the context of the component. It's going to be required to evaluate any argument you have associated with it. So this means that you have to have your specification of that component, you have to have the domain assumptions, and then you have to have the projection of those desired properties that you want to satisfy, and then you have to check against it. So you have to check that your machine learning component is doing what it says, you have to check that all your domain assumptions are correct and valid, and then you have to check that their combination is correct. You have to do all three of those things. Additionally, you have to worry about environmental assumptions. These are explicit statements of physical parameters frequently, which are outside the scope of design authority. You have no control over them. And you need to have these listed out to evaluate any safety argument. The thing to keep in mind with this, these have to be validated at design time and during operations. And that's the part we often forget. The assumptions may be valid at design time, then we field our system. Work as envisioned is not work as executed, and whoops, you violated an assumption, and then your safety argument no longer holds. Pictorially speaking, what I just said, you've got your component specification, your domain assumptions, your environmental assumptions, all of those things together should show that your safety requirements and your system requirements are satisfied. And that's that projection of those high-level aircraft requirements all the way down onto that particular interface of that machine learning implementation. I'm focused on safety. Just imagine performance is also there too. It has to do with it. Now, a lot of my friends say, well, what about architecture? Surely I can use architectural means and methods to help reduce my burden of showing that things are safe. And indeed you can. But please remember, it is not easy. And the classic example, we all think of the simplex architecture, courtesy of our good friend Louis Shaw. You've got a trusted component, you've got an untrusted component, and maybe you've got some sort of a switch between them. And folks frequently think, oh, well, I only just need to verify the trusted component and everything else will be fine. Not quite that simple. You first come up with a holistic argument. So you have to state, given a specified architecture, these projected safety properties and requirements will be satisfied by the component specifications and the domain environmental assumptions. And from that, you have to prove that your specified architecture is giving you that independence argument. Normally, you use an architecture to say certain things are independent of them, of one another. Essentially, you're trying to say that based on certain architectural principles, only certain components are relevant at a given level of design assurance. That means, for instance, only your trusted component needs to be at that level A of design, and your untrusted component may need to be, at a lower level of design. And from there, then you also have to make the argument in detail that each of your components are behaving appropriately. Now, one thing to keep in mind is there is no such thing as a free lunch. We do this today. We use architectural arguments to essentially do through redundancy, show that you have increased levels of safety. Given the level of design assurance attached to your function, you cannot just ignore the untrusted function. So what is it? ARP 4761A in Appendix P tells you if you have a function which has to be level A in assurance, and you're attempting to use that simplex architecture, any kind of switching architecture, the most credit you can get is a twofold reduction of assurance. So imagine you have level A, and pretend there's A, B, C, D, and E, 5 levels. One of your components, essentially the trusted component, has to be level A. Your switch has to be level A. And your untrusted component has to be level C. You can't go any lower than that. So keep in mind, it's not a free lunch, and you have to make this very thorough argument. The independence is important. For instance, both of your switch must be independent of your trusted system, must be independent of your untrusted system. No common modes of failure. And we can go into a little bit more detail about that, but you can get the general idea. If you've got a lot of complexity and a lot of interdependence, this is going to be a very complicated argument for you. Okay, so we've talked a little bit about explicit claims, how you might structure an argument for some explicit claims, how you might use architectures to help you in structuring your argument. What about the evidence that you're going to need to substantiate your argument? And please keep in mind, like I said, you do a whole bunch of tests. The results of your tests are not evidence. Those are artifacts. More is not always better. How do you go about generating the evidence you're going to need? And it's hard kind of to see what the problem is. You think, oh, I'll just do a whole bunch of tests or a whole bunch of sims. Let's talk about how evidence is used today. So physical components, it's very clear what you need to do. You need to have clear criteria for your physical components. So imagine I'm a screw on an aircraft. My criteria are simple associated with my screw. Those are failure breakage rates, mean time between failures. So if I snap, if I shear, I can figure out what those failure breakage rates need to be in order to get my overall target level of safety. And those are straightforward. The feasibility of testing is relatively straightforward. For physical artifacts, limited testing provides compelling evidence of quality with continuity of physical phenomena, allowing widespread inferences to be drawn from only a few sample points. Very fancy way of saying, if I take my screw and I twist it, or if I bend it, basically I'm well aware. First, it will deform elastically, then it will deform plastically. I do not need to twist it at, 1,000 pounds force, 1,001 pounds force, 1,002 pounds force. I only need to take a couple of points. I can draw out that curve, and then I can see where on that particular curve a particular screw is residing under a given amount of force applied. For deformation, you're going to see. Similarly, process and product correlation. The underlying principle of statistical quality control is that sampling a product coming out of a process gives you a measure of the quality of the process itself, which in turn then determines the quality of the items that are not sampled. Again, for our screw, I make 1 million screws. I sample 10 of them. I see how good they are. I put them under test based on whether or not they're meeting their required criteria. So as they say, are they deforming as we expect them to do? I can see, my manufacturing process was pretty good. And then that tells me the rest of the screws are also pretty good. Software. How does software fit into this this way of collecting evidence and making that traceability train? You have to remember for machine learning is simply a software implementation that flies on your aircraft. Its complexity and its interdependence on the domain and environment, as we talked about in the previous pictures, make it difficult to have explicit and precise articulation of criteria that is meaningful and that can be measured. This is a very fancy way of saying, what does it mean for your machine learning component to fail? What does it mean for software to fail? These are hard things to actually elucidate very clearly. So what does it mean to miss identifying a Persian cat? Does it mean that, okay, you misidentified the Persian cat? Does it mean that it was a stuffed cat? Does it mean that it was a mixed breed? So on and so forth. Feasibility of testing. This one's a no-brainer. Limited testing of ML does not provide a compelling evidence of behavior under all conditions. So if you only sample a couple of points in your operational design domain, you're not going to be able to say much about what's happening in the in-between points. Interpolation and extrapolation is non-trivial. And process and product correlation, obviously. We'd like to think more rigorous design processes associated with the design of machine learning components will hopefully lead to better quality machine learning components. However, this correlation is not sufficient as the sole predictor of evidence, as correlation does not imply causation. There are some very rigorous processes out there which do not yield, correct or rigorous results. The easiest one to remember is witchcraft. So you can use witchcraft, which is, of course, very rigorous if you're a witch, to attempt to predict weather. That does not necessarily mean that your predictions are correct. Okay. Now that we've spoken of witchcraft, let us move on to testing, simulation, and analysis. So how do we go about generating our evidentiary artifacts for our machine learning components? Where we're going to need to use everything in our toolkit. This is not a trivial or simple thing to be doing. Testing is indispensable. However, testing is insufficient, as it's unclear what coverage means in terms of machine learning components. There's a lot of work going on right now with EASA talking about specifying the operational design domain, but it's unclear how one arrives at the fact that one's operational design domain is actually complete. So, testing is good. You're going to have to do it, but you have to remember that you're going to have to supplement it. You're going to need to show, connection explicitly between your test performed and your properties claimed and the gap that you're going to have left. You're going to probably have to backfill it with sim and analysis, and sim and analysis can help you out with the validation of environmental assumptions or interface assumptions, feasibility of temporal behaviors, so worst case execution, for instance, verification of code implementation. Frequently, you'll be able to do something like simple logical coverage. Now, what that means is a different thing entirely. Checking that components in aggregate achieve their system level effects. You can sample a couple of runs and see if you're getting what you want. And that's a check to see that behavior is evinced. It doesn't let you say it's always evinced. And as we mentioned, sim and analysis in itself is insufficient frequently due to things like model inaccuracy, incorrect assumptions. We could go on and on. And this comes from the fact if you can't imagine the condition or if you can't imagine the phenomena, you're not going to see the behavior exhibited in your sim or even in your analysis. Similarly, formal methods, a good tool in your arsenal. It can help you provide some guarantees for your components, especially for components which are well specified. You can get some proofs of correctness there. I say this as a formal methodist myself. These techniques can frequently lack scalability and often require an expert to use them. That being said, you're probably going to have to use all these things in order to go forward. And indeed, you do. The first, I believe, stage 4 special issue paper has gone forward from Collins. So I'm not stealing anyone's thunder. And I believe it is an altitude hold implementation via machine learning. That particular function for fuel saving. FAA has indeed approved it. Of course, it's not actually flying on anything, and they did indeed use all 3 of these particular methods. Now, this was, of course, an analytical function, which allowed them to do a very thorough simulation and testing set of generation of artifacts, and they did have formal methods proof associated. Expertise. I've just spoken of our friends at Collins. They had a lot of it, and it was very necessary for them moving forward. You need to establish that your component, your machine learning implementation is going to be safe. You're going to have to do that through inspection and analysis of your safety claim, the argument associated with it, and the evidence offered in its support. So please remember, you're going to have that particular explicit claim we talked about. You're going to have evidence for those claims and a rigorous argument that links the two. As I've mentioned before in other talks, if not in this one, evidence without argument is unexplained. Argument without evidence is unsubstantiated. Any evaluator, that can be someone from the FAA or just a third party, has to be able to calibrate not only the technical claims and evidence. Just having that argument right is only half the battle, but the organization that produced them, because the integrity of the evidence chain is vital and cannot easily be assessed without supporting data. You're going to have to talk about the qualifications of the personnel involved in the development of your component, your machine learning implementation, the track record of your organization in providing these machine learning implementations, processes by which these components were developed, and processes by which data used to train or test that machine learning component is collected, curated, maintained, etc. So these are all almost as important as having the right argument and evidence. The big one, managing complexity. So simplicity does not precede complexity, but follows it. Your first design is probably going to be more complex than it needs to be. Only through knowledge and through experience can you simplify. I think that's an Alan Perlis quote. What this is getting at, please only implement machine learning when necessary. If you can implement your function another way, that's probably going to be your easier path going forward to certification. Your key to essentially getting your required amount of assurance at a reasonable cost is simplicity. And this includes not only simplicity of your critical functions, but simplicity in your system's interactions. So remember that. Feel free to put in all of the machine learning components that you feel like for non-critical functions, but then remember you're going to have to bound their interactions with other critical functions. Using architectural means is certainly a good way to mitigate complexity going ahead. And this is not just the simplex architecture type argument I'm talking about. I'm talking about integrated modular avionics. So if you partition your computer or your architecture into containers whereby all of your safety critical level A functions are in one container and all of your non-safety critical functions are in other containers and all of your machine learning components are in an isolated container whereby they cannot influence anything else, you're probably going to do quite well. And that's essentially establishing independence, so system-level properties are guaranteed by individual components which preserve that emergent property despite failures in the rest of your system. So if that machine learning container goes away, if the rest of your system executes without flaw, then hey, you've got an argument to make to a regulator. And please attempt to use some sort of standardized process or some sort of repeatable process when you're developing your machine learning implementation. You need to preserve the chain of evidence on which you're going to base your argument surrounding that machine learning component that it's meeting its requirement. If you don't have that auditable chain of evidence, you're going to have a very difficult time convincing someone that the component exhibits only its intended behavior and no unintended function. And that's going to mean you're going to have a very hard time proving that your emergent properties are actually preserved. We can talk a lot more about that. That's one of the key barriers. I'm going to take a sip here. We're almost done. All right. Some questions, which I and the FAA and EASA and other folks, so I should not be speaking for the FAA, which I believe that need to be looked into. The first one, the most obvious, how do you know when a machine learning component's behavior meets its requirement? So how do you know that your training data set is of sufficient size and represents sufficiently the operational design domain? So how do you know you've got all of those corner cases in it? Accuracy versus generalizability. So this is the variance bias trade-off. This is well known. How do you know when you've trained enough? How do you know when you've validated enough? How do you know when to stop? And what constitutes an actionable specification? And I think there's a comment on that one later, but if your machine learning component or implementation is recognizing Persian cats, what is the set of requirements associated with identifying a Persian cat that is actually non-trivial to extract from a big old pile of data? What are the limits of current processes and metrics currently used in developing and evaluating these systems? How to use testing. So what is the meaning of testing in terms of machine learning? Can we create logical-based oracles which can be used in test for a machine learning implementation? What is the value of simulation? How many billions of miles are you going to need to drive with your self-driving car to show that, oh yes, indeed, my model contains all of the phenomenon that I needed to? What is the use of formal analysis? If you have an analytic function, you're going to have a beautiful proof. If you don't, what does that mean? Runtime verification frameworks. This is like envelope protection. This is great if we know the envelope, and more importantly, we can detect a violation of that envelope in sufficient time that there is a mitigation action that can be executed that drives you back into the safe set. If that is not the case, then you have to try to think what is the true value you're getting from your runtime verification framework. Question 3, which is one which all of you guys are experts in. What are the set of characteristics and parameters for your machine learning implementation that allows you to bound the behavior of the overall system? Things to consider when you're looking at these bounds. What are the data information quality that you're going to need? What are the particular architectures you're going to want to consider? What are the associated metrics? This is a big one. What is a measure of being close to a boundary? What is a measure of exceeding a boundary and by how much? What is the minimum set of information required to reconstruct and audit a machine learning implementation in the case of an accident? This is kind of the last big thing I'll talk about before finishing up. This is an incredible problem. The NTSB and NASA are working on this. It boils down to the second question. How do you create an encoding scheme that would reduce the volume of state information associated with your machine learning implementation into a tractable compact form? And this is the data compression problem. So if you can solve this problem, you can solve the data compression problem perfectly. This is an open question for forensic analysis. I certainly welcome your thoughts. Other questions, not quite as exciting perhaps, but actually very relevant too. Information assurance, a big thing, especially for our security friends who are looking at not just the data fusion and data collection problem, but data poisoning, drift in data, especially for retraining. How is change managed? Again, something very important in terms of maintenance. Not only configuration and version control, does this kick off a full recertification effort? Actionable specification being abstracted from a big old pile of data. How do you do that? This is an open and non-trivial thought. And then when can machine learning be used in design development and offline accident or incident processes? You thought, oh, but that's already happening. It is indeed, but there are tool qualification problems or issues associated with it. So again, we could go into a lot of detail there. All right, deploying, going forward, simple thoughts here. Just start in an offline fashion. Start with simple, well-defined, non-safety critical applications and go from there. Then progress into your embedded flight operation systems. With offline learning only, you freeze your system and then online it goes. Start with functions which have clearly defined requirements, a very unambiguous means of checking the answers or outputs of that function, and a means of intervention and mitigation for incorrect answers and outputs. Those are going to be those low, I hate using the phrase low-hanging fruit, but those are going to be the easiest functions to tackle first. Similarly for standards, there are ongoing efforts. I'm involved in a couple of them. Standards need to be targeted in areas where there are gaps. We've already got some standards out there. Use what's there. It's only when you can't use what's there, try developing a new standard. And you need a measured approach for the development of these particular standards. We need to standardize criteria for what constitutes sufficient evidence. The easiest way is going to be looking at a function which has a traditional implementation, one which has a machine learning implementation, and then coming up with an equivalence between the evidence which was accepted for that traditional implementation and how that translates to machine learning implementation. And lastly, takeaways, deployment and standardization should, proceed methodically. Premature efforts to deploy and standardize may end up jeopardizing paths to transition. It may create technical debt or set back the entire aviation industry. And with that, I shall stop for questions.
Thank you very much. This was very interesting. Let's see if the audience has questions.
Not as technical. I was thinking of putting a formal methods proof in it, but I thought, no, that would just get Petros annoyed.
Hey, good morning. This is Kevin Wise. I have a question I dialed in late. I enjoyed what I saw being presented. Some of the, I'll just say this, and it seems like a lot of people are using control barrier functions to protect inner loop. I'm going to bound my aircraft state space using a CBF. I got machine learning on the outside, thus I'm safe. But I didn't see that you addressed that. Did you talk about that in your talk?
I did not address it specifically. I would have lumped that under the formal methods section. So we are doing work with the AFRL, specifically with Carrie Ann Hobbs, and they've got an SBI, not an SBIR. They've got a grant going with Caltech, looking at that specifically for a flight test. Control barrier functions are extremely powerful. The trick there, of course, is the complexity of the barrier function. And some particular functions are very clean. It almost falls back to the same problem with the architectural mitigations. If you have a very easily specified barrier function, then the implementation of that function and the checking to make sure that it is actually providing the protection it is supposed to becomes relatively straightforward. For complex barrier functions, it's a little bit harder to go forward and make that argument. And I know I'm being a little bit weaselly in those wording, but I can speak to a couple of examples we've run into. But if you have a very simple, clean specification of your system, and that allows you to develop a very specific and clean barrier function, then you're on your way. This is not always the case because the complexity of interactions often degrades your ability to clearly mathematically specify that barrier function.
I'll just tell you, I have an opinion about this. So we've been looking at CBFs, and the implementation that we've implemented, it's really a switch to a different control law. When the CBF gets active, it basically ignores what you were doing and then implement something that keeps the states bounded. Okay. What's to say that when you get back in your set that the machine learning is doing anything correct still?
Yeah.
Yeah. So in a landing situation, this could be very serious. Okay. So I would just, and we see like this ULI and, the one at Stanford, a lot of the ULIs are relying on CBFs, and there's Control System Magazine articles. They're all over the place, Yeah, I'm very interested in understanding how FAA or NASA, what their opinions are on how that progresses. This is very important research, so I'm not trying to belittle their use. I think it's quite interesting, but it doesn't seem to me to really answer the question of provability that the machine learning is safe. Okay, over.
No, that is an excellent comment, and I would love to email you a little bit about my thoughts. All right. Any further interesting, excellent questions? I see Irene.
So Natasha, I'm going to pull back a little bit on this and ask sort of your opinion. Again, you're not to be held responsible, just an opinion. There's one thing to try to put a lot of this stuff on transport aircraft, which is very methodical and understand the aviation, right? That's one. But there's another aspect of it, right? There's a great deal of academic work in pushing autonomy, machine learning, etc. And so the question becomes, is there something that can be done without going through all the specifics of certification to push that technology along? Let me give you an example. So we talk about it. I'm going to, since Mike Atchison is here, he can correct me when I try to quote him about perception of a pilot, right? Let's look at perception systems. And Mike would claim pilots see crap. Is that a fair statement, Michael?
It depends on the day.
So let's assume that that's correct. And yet we expect a perception system on a UAV to see everything, and to whatever degree, and that's not realistic, right? So is there a way the academia can start exploring certain systems? For example, perception comes to mind because even as an advisory system, it is absolutely, I think, necessary for safety. Is there something that they can do in trying to explore and field those systems in whatever would be considered a relevant environment to help push that technology forward, and with understanding that just because something flew on a 55-pound drone, that doesn't mean it's going to go into 787 tomorrow, but it's going to make that technology closer to being ready to make that jump. Does that make sense?
Yes. No. And I've been doomy and gloomy because mentally everything in my life is a level A part 121 function. Level D. So again, I haven't explained these levels, but imagine there's 1, 2, 3, 4, 5. Level number 4, you go down to level D. Level D is just kind of a high-level black box testing you're going to have to do for software. So less safety criticality in your function. If you're not using that function for something safety critical, or if you have another means of doing that function, then the world is your oyster. As they say, you can fly something along as North Sea, no safety effect. Alternatively, you can say, imagine I have, and again, I should preface this, our friends at Honeywell are doing it. You have 2 systems for perception that they're looking at and untangling the requirements. So basically hitting the landing for an eVTOL, you paint an H on a vertipad, and you have to, by some means identify that H and land on it. You can have a perception system, which you have trained through an ML fashion to do the implementation. And you can have a pure deterministic vision system. And then they're, doing a back-to-back comparison of those 2 things. And so essentially, if you fly both and you have a pilot on board, you have 3 things. You've got the useless pilot eyeball on certain days, but also useful for detecting geese which are wandering across the H or snow or something. You've got a very clean vision implementation, which is going to parse out, what is the sensor problem? Essentially, are your sensors, coming to the right, the right fidelity? Are you getting the right information? Because the software can be verified in a traditional, or essentially done via DO-178C in a very traditional fashion. Expensive, but can be done. And then your machine learning implementation, where, kind of, it could be doing what it's supposed to be doing. It could be doing completely other things. And by doing sort of this tripartite approach, you can field certain systems, you can gather data, And then you can attempt to then parse out what are the contributions to safety, to intended functions, to unintended functionalities from each of those separate means of implementation of the function of can I see an H underneath me? I'm going to stop. Is that what you were looking for, or were you looking for a different kind of path forward?
No, that's what I'm looking for. Part of it is I'm trying to help establish for our friends in academia a way that they can contribute to moving the technology forward and have the aviation industry adopt a lot of things maybe faster than they would in the traditional way and help contribute to it. As opposed to, this is all great and we get funding, but a lot of our friends really want to make an impact in the real world. And so I'm trying to help chart that pathway for greater impact with our industry.
Yeah, and that's going to be non-safety critical functions. The Collins example is the top one. They had a clear means of implementing their altitude select. It was a fuel efficiency problem for them. They had a traditional way of doing it. They had a machine learning means of improving their efficiency a wee bit, but they were able to bound it analytically, and that enabled them to move forward and show, look, this is A, not a safety critical function. B, we have a means of showing that it's doing what it's supposed to do. And C, we have a means of showing that our evidence is sufficient. So as they say, looking for those sweet spots, those types of functions, which may not be the most wild and exciting functions to begin with, but are still valid use cases for the tools and techniques you're going to learn or need, not only from the development side, because I think I saw a cyan on one of the other pictures, but also from the verification and validation side. And both of those have to be advancing at the same rate.
Hey, this is Kevin. I'll just say I agree with what you just said there. So, and you said it earlier too, introducing this into the aviation industry in non-critical, non-safety critical areas is the where we need to start. And then that's the only way to really build trust. I see Louis talked about, the use of ML and these kinds of techniques in sensor processing. That's kind of a key area. Boeing's been making a lot of progress in detect and avoid, where we have a radar for the WISC vehicle, to support that mission. And the use of these technologies in doing the sensor processing is critical. Now, what's really a challenge, even though I'll say that this technology has been used a lot in sensor processing, we're taking these radars now and you're looking, typically they look up or they look out, but now you're looking down and you've got so much, the whole world is different, right? And so, yeah, it's still, and we're finding it's a real challenge still, Yeah, okay. So thank you.
No, excellent, well-made point. And I should have called out, we too have a Space Act with WISC, and yeah, they've got some interesting ideas going forward. So, all right, I see a hand up, Sandeep.
Hi, yeah, I'm a postdoc working with NARA, and this question might be related to what Irene is saying, and maybe it's embedded in your slide somewhere. But the guarantees on these ML methods are generally on distributions of training data sets, right? And they say like terms that it's going to be inaccurate n in a million samples, but you cannot demonstrate a million trials due to cost and time constraints. So what does it translate to demonstrations, right? And it is equivalent to seeing when a human pilots a commercial aircraft, you say that the human is certified good if he completes X number of man hours. So that million is getting translated to some man hours, and you're saying, okay, that's fine. But what does it translate to demonstrations?
Yeah, and this is where you want to be very, very careful. And there was that slide talking about what is the meaning of a single simulation run, or what is the meaning of a single test run.
Right.
And you don't, as they say, it's very easy to jump into the idea of, let's look how pilots are trained, because I'm moving a pilot Part 91 function now into a Part 25 function, 1309, equipment and systems. surely there's a direct equivalency. That pilot is imbued with a great deal of common knowledge and a great deal of training outside of his pilot training. So, as Mike will say, because he's a pilot, I'm a useless pilot. He's a real pilot. I'm just a wee baby pilot. When they evaluate you, they weren't actually evaluating how well I could fly. They were evaluating how trustworthy I was, how risk-taking I was. And so you have to realize you don't want to try to make that equivalency. Instead, you want to look clean slate. What does it mean to have a piece of test information about this particular machine learning component? And what does it mean to have coverage? And for certain types of functions, all you're doing is you're testing against a requirement. And if your requirement says, I must have no unintended behavior. If you can, as they say, come up with a magic test which shows you have no unintended behavior, then you're golden. But what is that magic test? As Dijkstra says, you never show the absence of errors, you only show their presence. But as they say, the thing to keep in mind, testing is very good to show, I have seen this behavior once, or eventually this behavior comes, or given a worst case execution time, this behavior may still, be evinced, 50% of the time, or, something like that.
Okay.
And so it's the type of requirement you're testing against, or it's the type of requirement you're attempting to satisfy, which will determine, is testing the right evidence for me? How do I go about building my argument, showing that these test cases actually are evidence and not just artifacts, just big old pile of data?
I see. So it would be helpful that you also create the worst case scenario and test that on that scenario to certify a particular ML component.
So context. So okay. The context is what you're really looking for. If the context is such that test case or a suite of test cases show that particular claim is being met, that's how you show that there's value to doing those tests.
Okay, thanks a lot.
Yeah, and to give you an idea, I think Collins was forced to do sim and test analysis. They did over 1 billion runs. So it is burdensome.
So Natasha, sorry, to follow up, there's a lot of work that's going on where people are beginning to try to look at some of the machine learning approaches in the context of, let's say, control theoretic tools, right? So since we have really robust theory, we usually know when things break down and how they break down. If you have methods in machine learning that can be shown to be basically characterized in terms of, let's say, control theoretic, and you have those bounds, how valuable do you think that would be in creating a safety case / providing evidence that we understand where things break down and how they break down, even though the methods themselves may be statistical and distributional?
Yeah, and this is an excellent point you've made, Irene. I liken this to using formal methods or formal proofs. So, there are 2 points or there are two important parts of creating your safety argument. One is making sure it's logical and follows through, and you have substantiated with evidence. 2 is convincing someone that your argument is true. And so for part number 1, your bounds, your understanding of the underlying physical phenomenon, obviously this is important. You've developed your proof, you've developed, the underlying physics of the situation, you've shown why you should be obeying this particular bound, and then you've developed some statistical argument related to it. Now you have to convince someone who, I like saying is probably a lot like me, and, not very bright, doesn't have a lot of, background in what you're doing, but, has a good nose for when something is going to be safe and when something is perhaps not fully considered in terms of exceptional or off distribution or off design domain particulars. And that's where you're going to have a very, very clear way of saying, what is the particular value of that statistical argument? And so again, this comes from saying, imagine I have a distribution of inputs and my distribution is Gaussian, and I can show that, to 5 nines, indeed, I've looked over my distribution. Someone like me is going to say, well, yes, but if those remaining cases, those remaining nines you don't have, all lead to catastrophic failures, your argument is not compelling. But if you're able to say, no, this is a particular, set of tools and techniques, which I can show work as well as has been shown for 50 years of control theory. And the consequence of getting it wrong is such that I can always either detect it, or I can always either mitigate it, or it's such that it can be risk which is absorbed through other components in my particular architecture. Then your ability to have these particular bounds becomes very valuable. So again, it's going to be a context argument, and it's going to be your ability to explain it to someone who was a non-expert in that particular set of proofs.
Thank you.
All right, I feel I have depressed everyone, but I'm really actually excited about machine learning. There are a series of special issue papers going through the FAA, which are slowly beginning to transition some of these things into the NAS. I just go forth for my agency and proselytize, just telling people, be careful, be careful. But I think there's an enormous future going forward here. It's just making sure we take it in the small, reasoned steps that allow us to have the successes we need, and perhaps not to dive into some of the harder problems before we get cut our teeth and get our feet wet on the easier problems, which will allow us to thoroughly evaluate the techniques we're using and the means that we have to validate and verify them. With that, I'll shut up. All right. Any last questions? I've eaten 15 minutes of your time. I owe you all a quarter hour. I'll have to go to UIUC and buy you all a coffee.